and I'm Michele Grisafi, a PhD student in Italy, Trento. And today I would like to present a paper I made in collaboration with a few colleagues, Mahmoud Ammar, Marco Roveri, and Bruno Crispo. The paper is called PISTIS, a trusted computing architecture for low-end embedded systems. And I would like to start from the issue at hand, which is embedded systems, which we all know that they are at security risk, reason for which in the past several security solutions have been proposed, with the most prominent one probably being security services, such as remote attestation. However, these services are usually enabled by trusted execution environments, or TEs, which we all came to love. However, if we take a look at the state of the art on security services and on trusted execution environments, we can see that we have a wide variety of options, which some of them which are hardware-based, being able to provide strong security guarantees and good feature set. However, we can also see how there is a clear gap on the graph. A gap populated by all of those devices that maybe they are legacy or they are too cheap, which do not have enough hardware resources to have these higher-end approaches and must use software-based approaches. However, the current state of the art on software-based approaches do not provide enough security guarantees and good enough features, reason for which we try to come up with something that could actually fill this gap. And this is PISTIS, which it is a trusted execution environment made supposedly to fill the gap. How do we do that? By bringing some of the features of higher-end solutions, such as interrupt support, DMA support, support for trusted applications, and bringing it to devices that do not have hardware resources. For instance, they do not have memory protection units or memory management units, obviously, and are not even compatible with hardware modifications because they are either too expensive or unpractical in many scenarios. So this is exactly what is PISTIS, and I would like to answer two questions now. What is, when do we use PISTIS and how does it work? As for the when, it is quite easy. Let us consider a typical scenario in which we have a microcontroller unit, so an MCU, which is programmed by an untrusted party, and in this case we might have a network attacker which will try to bring havoc to the system maybe. We do take denial of service after the scope, but as for the rest, we have to have some kind of protection for the attacker. And that's what PISTIS can bring, protection using a trusted execution environment, as long with some trusted applications, so some security services. And let's see how, step by step, we do this kind of security, how we protect this device. And we have to start from an empty MCU, and on top of which we have to deploy in a trusted manner our trusted execution environment, which is software only. So it is a runtime library and some trusted applications. We provide implementation for security, secure code update and remote attestation, which are two of the most prominent ones, but this is compatible with other trusted applications. And as soon as we have the MCU with PISTIS up and running, what we can do is to give the control back to the untrusted application programmer, who will be provided with our toolchain, our custom toolchain, that can be used to create the binaries, the untrusted application, and can be used to deploy it through our secure code update security service. At this point, we will end up with an untrusted application running alongside PISTIS on the microcontroller unit. However, at any point in this process, the attacker could play a role, could try to perform several types of attacks. Runtime attacks, man in the middle maybe, trying to corrupt the toolchain, or why not inject some malicious code inside the source code. And what you would do normally in a normal scenario is you would run a remote attestation and to see whether the application has been compromised. However, on these kind of devices that we target, we do not have the hardware securities that allow to isolate the the security services from the malicious application. So we have no way to make sure that the remote attestation can work without being interfered with by the attacker. And that's what we do with PISTIS, is exactly a memory isolation primitive that's designed to isolate the malware from the trusted execution environment and its applications. So that we, for instance, can execute remote attestation without having to worry about the attacker at all. But because I want to give you more details, let's try to go into the memory isolation. Let's follow the rabbit hole. And memory isolation it's a matter of policy. It is a policy base. And what we have to do, it is a three-step process that starts with dividing memory, the initial empty memory, in different regions, some of which will be assigned to the PISTIS, to the protected code, some of which will instead be assigned to the untrusted application. And as soon as we have this logical separation, what we have to do is to deploy, of course, both PISTIS and the untrusted application in the right segments. However, this is not enough, because even if they are separated at deployment time, there is no guarantee that at runtime the application will not try to break free from this isolation, for instance, trying to perform some memory accesses. And that's why we need to have the last and final step, enforcing an access control policy, which, in other words, means to limit the type of memory accesses that the application can perform on the rest of the memory. And for the sake of this presentation, let us focus on the execution privileges, which will, in our case, we want to make sure that the application can only execute either its own code base, obviously, or some entry points in the PISTIS runtime library. And how do we do that without hardware? Because that's a real question. And we have to have a software-based approach, so no memory protection unit, for instance. And to do so, in software, we use instrumentation and virtualization, which in simpler words means to make sure that each and single instruction inside the application binary, it is compliant with our access control policy. And let me give you an example of how things work in practice. And let us start from a sample code in assembly containing two functions, two instructions that are calling a certain function. The first one is a function which is in the application code base, so it's fine. The second one is a function whose address is contained in a register, R10. However, we have no way to know whether the content of R10 at runtime will be safe or not. It could be, for instance, an address in the stack, something that we want to prevent. So what we have to do is to instrument this code and virtualize the last function. To do so, we use our custom toolchain, which will take care of replacing all of the unsafe instructions with safe alternatives. So in this case, we, for instance, replace the call to R10 with a move, so we store the content of R10 to a safe register, R4, and then we pass the control to the TCB with a call to a virtual function, which will make sure, it will be taken care of by the PISTIS at a later stage. So as soon as we have this virtualization, this instrumentation, we can indeed deploy the application. But rather than starting it right away, what we want to do is to perform a binary verification to make sure that all of the unsafe instructions have indeed been replaced. And if they have, so if we run our verification and all of them pass the checks, we can run it safely. However, why do we need this binary verification in the first place? And the question is, it allows us to have a stronger attacker model with an attacker who could be able to bypass the instrumentation and deploy an application that contains the unsafe instruction, the call to R10. And in this case, it will not be a problem because these will fail the verification and it will be rejected. However, if we indeed have a compliant application that is deployed, we can run it. Still, our work is not done yet because, again, what is the content of R10 at the end? And to know that, we have to perform some safety checks inside our virtual calls, which will make sure that the original content of R10 is safe. If it is, we call it. If it not, we stop it. And that's basically how we do that in software. And we do similar things with other types of instructions. But if you're interested in more details, please refer to the paper, which also contains details on how we make these mechanism work with DMA operations and interrupts, which were some big challenges. So now, of course, software, it's fun to have a software-based approach, but of course, we have to pay the performance. And speaking about performance, we evaluated our implementation on a TI MSP 430 MSP, microcontroller unit, with a set of 13 embedded applications of different types, also including a TI official benchmark. And what we see that we measured mainly three metrics, which is a memory footprint, runtime overhead, and deployment time. And you can see how we indeed have high overhead, both in terms of memory and on runtime execution. And however, there are two things to be considered here. The first thing is that it really depends on the type of application that we want to instrument, with some of them having very small overheads. The second thing, the most important one, is that in many scenarios, especially in embedded systems, this is acceptable. For instance, if we spend a lot of time sensing or transmitting or receiving on a high latency network, this instrumentation will not affect that part of the system. So in the end, we will not have that much overhead in our final application. And but even if we do have overhead, we still manage to shrink down the deployment time overhead. So that's on a positive note. We brought it down to decreasing it by 73% by using optimized binary format that allowed us to shorten the time. So if you are interested in how we did things, please check out the public repository on GitHub. Here's the QR code, or you can find the link in the next slide. And feel free to play around with it. So, to conclude, I just wanted to recap briefly what is PISTIS to answer the three big questions when we are talking about the security thing. So, why do we need it? What is it? And how does it work? As for the why, again, there is a security gap that must be addressed, must be filled somehow. And we do this using PISTIS, which might be the cheapest available option out there, because all of the rest is hardware, or might not be good enough. As for what is it, again, is a trusted execution environment with support for both trusted applications, such as remote attestation, and to secure DMA and interrupt operations. And finally, how does it work? By using a policy-based memory isolation based on a software-based trusted computing base. Finally, how does it work? Again, with software instrumentation and virtualization, which allows it to work without any hardware whatsoever. So thank you for your attention. I really appreciate you joining us. And here's my email address if you want to email anything. And if you have any questions, I'll be happy to answer here and now, or just approach me later. It's up to you. So thank you very much, and I'll leave the floor for some questions.